In this video, we'll be going over instantaneous velocity. So, instantaneous velocity tells us how fast an object is moving at a really small stretch of time, or in other words, at an instant. Hence the name instantaneous velocity. Basically, instead of taking a displacement and dividing that over a large period of time, like we would do if we were calculating the average velocity, we want to take that time frame and make it as small as humanly possible. So the displacement traveled over that small period of time is going to be the instantaneous velocity. So if we take our average velocity formula, which is v average is equal to delta t, delta x over delta t. To get the instantaneous velocity, we want to take our delta t, or our time interval, and make it as small as humanly possible. Essentially, we want to make delta t as close to zero as possible. The closer something is to zero, or the closer a number is to zero, the smaller that number is. However, we don't actually want delta t to equal zero, because if delta t were to equal zero, then there would be no change in time, and therefore there would be no velocity at all. Also, if delta t were equal zero, then we would have a zero in the denominator, which would make our velocity undefined, which is not allowed. So we actually don't want delta t to equal zero. And so we want a segment of time as small as possible, but not so small that it's actually zero or non-existent at all. So let's look at this concept using the graph to the right. So let's say we have a simple velocity curve showing us the object moving with respect to time, right? So how the object moves with respect to time. So the y-axis, which is the vertical line, right? The vertical axis tells us the object's position in space, so where it's at. We'll label this axis x for displacement, right? And then the horizontal axis, right, tells us at which point in time the object is. So we'll label this axis t for time. So the vertical axis tells us where, and the horizontal axis tells us when. So let's take 2 points on this velocity curve, which we'll call v. Let's take point 1, and then let's take this point up here. Let's call this point 2. So now each point has a coordinate pair that tells us both its position and its time. So both x and t. So for point number 1, it's going to have an x coordinate and a t coordinate. And the x coordinate we'll call x sub 1, and the t coordinate we'll call t sub 1. Likewise, for point 2, we'll call its x coordinate x sub 2, and then we'll call the y coordinate, the t coordinate t sub 2. And so between point 1 and point 2, the object has changed both its position and its time. the displacement, or rather the distance traveled, is delta x, and the time traveled is delta t. So if we were to take this distance from here to here, this distance would be delta t, or rather delta x. Likewise, the distance from, or rather the space from here to here would be delta t. And so if we were to take a line and draw it between these 2 points, the slope of that line would be called the secant line, right? So let's draw a line in between these 2 points, points 1 and point 2. So if we take our green marker and draw the line through these 2 points, the slope of this line would be our average velocity, right? The slope of that secant line would give us our average velocity. And so why is that? So if you recall, the slope of a line is the rise over the run, right? The ratio of the vertical change to the horizontal change between 2 points. So let's write our slope formula. M equals y sub 2 minus y sub 1, which is our rise, and x sub 2 minus x sub 1, which is our run. And so we have our vertical change, which is y sub 2 over y minus y sub 1, and our horizontal change, which is our x sub 2 minus x sub 1. And so the thing is that we don't actually have y and x values, right? In this case, we have x and t values. So we would have to replace these values with x and t. So instead of y sub 2 minus y sub 1, we would have x sub 2 minus x sub 1, which is our vertical axis, the values of our vertical axis. And then instead of x sub 2 minus x sub 1, we would have t sub 2 minus t sub 1, which is the values of our horizontal axis, right? So x sub 2 minus x sub 1 is the same as saying delta x, right? Which is just a change in x values. And t sub 2 minus t sub 1 likewise is the same as saying delta t, which is the change in t values. And so now we have delta x over delta t, which is the change in x values over the change in t values, or in other words, change in displacement over change in time, which is going to be the same as the formula we have up here, which is the formula for our average velocity. So now we can just say that delta x over delta t is the same as the average velocity, and this is the reason why the slope of this line is going to be the same as our average velocity. And so the slope of this line right here, which we call the secant line, is going to be our average velocity, which in this case, it would be average velocity is equal to x sub 2, which is going to be 9, minus x sub 1, which is going to be 1, divided by our delta t, which is going to be t sub 2 minus t sub 1, or in other words, 3 minus 1. And that's going to be equal to 8 divided by 2, which is going to be the same as 4. So that our average velocity between points 1 and point 2 is going to be equal to 4. Now, if you remember what we talked about earlier, what we wanted to do was find the instantaneous velocity. So to find the instantaneous velocity, we have to shrink delta t, or make delta t smaller, right? So if you remember, we want delta t to get close to 0, right? But not actually equal to 0, right? So we want to keep this in mind. So let's try and shrink delta t, right? So right now, delta t is equal to 2, right? So delta t is going to be 3 minus 1, which is equal to 2, right? That's going to be our delta t. So let's try and shrink delta t to 1 instead. So let's go ahead and make this delta t from here to here, right? This is going to be our new delta t, which is about 1. So now we have a new x sub 2 and a new t sub 2, right? Because point 2 is now moving closer to point 1. So now we have a new point 2. Let's draw it in orange. So here's our new point 2 over here. And now we have a new x sub 2 and a new t sub 2. And so if we were to draw a line in between these 2 points, we would get a new secant line. So this orange line is going to be our new secant line. So, and the slope of this new secant line is going to be the new average velocity between points 1 and our new point 2, which is going to be in orange, right? And so if we were to take that new average velocity, it would be 4 minus 1 divided by 2 minus 1, which is equal to 3 over 1, which is equal to 3. So that's going to be the new average velocity between point 1 and our new point 2. And if we were to progressively shrink delta t, point 1 and point 2 will get closer and closer and closer together, as you would probably imagine. And so eventually, when delta t is really, really, really close to 0, point 1 and point 2 will be so close together that they will virtually be on top of each other, and virtually indistinguishable from one another, almost as if they were one and the same point. And so we make an approximation and say that the distance between point 1 and point 2 is going to be 0, right? So let's say that delta t is really, 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 really small, so that it's really, really close to 0. Point 2 is now going to be somewhere over here, really, really, really close to point 1. And so since the distance between point 1 and point 2 is so small, these two dots would be almost on top of each other. And so the line going through these 2 points is going to be called the tangent line. Tangent line. And the tangent line is just a straight line that just touches the curve at a point, right? In this case, point 1. And so therefore the slope of this new line, the tangent line, is going to be the instantaneous velocity, right? So let's go ahead and draw that tangent line. Let's draw that tangent line in the color blue. So that new line is going to just touch the curve at this point. So that's going to be our tangent line. And now the slope of this new line is going to be our instantaneous velocity, which is basically telling us how fast the object is going at the instant of time at point 2. Right? And so to find this slope, we have to take the limit. Right? And to be more exact, the limit is going to be the limit of delta x over delta t as delta t approaches 0. Right? So this says as delta t approaches or gets closer to 0, right? So as it gets smaller and smaller, what value does the function delta, which is going to be delta x over delta t, right? This is going to be our velocity function. What value does that function approach, right? So the slope of the line is going to be around 2, right? If we were to take the slope of this line, even though you can't really see it, the slope of this line is going to be around 2, right? And so therefore, the limit as delta x over delta t as t approaches 0 is going to be equal to 2. And thus the instantaneous velocity at t equals 1 is going to be 2. And so this limit is also known as the derivative. And the derivative is going to be the same as this limit over here, right? There's going to be no difference, no distinction between this limit over here and the derivative, right? And so that derivative, right, we'll call that derivative dx over dt. Right, so this is our limit, and this limit is going to be the same as our derivative, which we'll call delta x over delta t. And so the d in this case stands for delta. However, d is going to be an infinitesimally small change. So dx over dt is going to be the derivative of x with respect to time, or in other words, our instantaneous velocity.